Good morning, dear students. Welcome to the final session of this analysis and design of algorithms. Okay. So today I am going to make some discussions related to module 5. Okay. So module 5. Today I am going to make the discussions. Under this we have coping with algorithm power. Is the topic. Under this we have backtracking, and another technique is branch and code. So these are the topics what I am going to make some discussions today. So first of all, I'm going to discuss the concept of backtracking. So what is backtracking? So what are the different type of problems linked to the backtracking? So I'm going to share the PPT, just go through them, then we can solve some problems on that, okay? Okay, the slides are visible, I hope. So the topic is coping with the limitations of algorithm power, okay? So, of course, there are so many different type of problems we have to encounter, in particularly combinatorial problems like NP-hack problems. And along with that, approximation problems and strategy-wise problems can be also used to solve by using the combinatorial combination, that is in particularly coping with algorithm power. So, on the different strategies or different type of problem solving techniques like exhaustive search, what we have already made some discussions. No requests here. The request come here, I will allow. Okay. So then we have dynamic programming, and of course we have made a lot of discussions related to the dynamic programming in our previous class, like knapsack problem, Warshall's problem, and we have binomial coefficient and all those things. Next to today's topic, we have to more and more focus on backtracking. So what is a backtracking? So how it is used in order to solve the different type of problems. So backtracking, as the name suggests, so you have to create a state space tree. Okay, you have to create a state space tree, and you have to start from the root node. Okay, and you have to prune. Pruning means you have to grow the tree. Okay, so towards the leaf nodes. Then, whenever you found that if the solution is not at all possible, you can come back to the previous node. It's called as a backtrack, and you can reach the root node, and once again you can traverse towards the other end of the tree. So this is how the backtracking will work. Okay, so it will yield the solutions. Okay, it will give a solution to the reasonable time, and After the backtracking, we have branch and bound, which is one of the refined version of backtracking is called as a branch and bound. Means in backtracking, the pruning or the growth of the tree is without any constraint. On the other hand, in branch and bound, there is a predefined criteria. Okay, on the basis of which we can prune the state space tree. So I'm going to solve the problems. You come to know how this will work. So that is a definition of the backtracking. So what is the backtracking? So construct the state space tree. So you have to construct the state space tree. So remember, this is very, very important with the perspective of examination also. Definitely you will get one question from backtracking. Either it may be NQueen problem or it may be a state space sum of subset problem. Okay, in both the scenarios you have to solve, you have to draw the state space tree. This is really important and very, very important with the examination perspective. So next we have nodes, so called as a partial solutions, and as well as edges. The edges can be considered as a choices. Choices antandre we can extend anta. So next we have pruning. Pruning antandre ಏನಪ್ಪ? It is nothing but the process of growing a tree. Okay. So non-promising nodes anta karitivi. So what is promising and non-promising? Promising nodes are those nodes through which we can get a definite solution. On the another hand, if you have a node and if you grow in that direction, if it is definitely when you are not going to reach a solution, the given node can be considered as a non-promising. Promising means getting a solution. Non-promising means definitely when you reach the end, you have to backtrack because definitely you won't reach a solution. So now I'm going to take a problem here, so called as a NQueen problem. So this is really important in the examination. They may ask a question like this: solve NQueen problem using backtrack with suitable algorithm and as well as state space tree. So they may ask a question. So the probability is around 90 to 95% of this question. So that is why please give more and more importance about this. Okay. So place NQueens. So how to solve this problem? Place NQueens on a n by n chessboard so that no two of them are in the same row. So we have to place 4 queens on the board here. You can see the 4 cross 4 grid here, and we have to place the 4 queens on the chessboard. But there is a condition. So I can place a queen here. I cannot place the same queen in the same column, or in the next I cannot place the queen in the same diagonal also. I cannot place the queen here also. Means if you place a queen in a given box, you cannot place another queen in the same column, same row and diagonally also. So this is the challenging task. Okay, I have to place 4 queens on this board. But the problem is that I cannot place 2 queens on the same column, same row and diagonally also. So now how to solve this problem? This can be solved by using the state space tree. So let me explain this using the board also. Okay, so just see how this can be solved. So this is called as NQueen problem. So how to solve this problem? So let us find out. So I have to place the 4 queens now. Okay. I have to place 4 queens on this chessboard. Okay, because this chessboard is of the dimension 4 cross 4. 4 cross 4 means we have 4 rows and we have 4 columns. Okay, so now how to place the queens here? The condition is that the first condition is no same row. We cannot place them on the same row. Next, no same column. I cannot place them column wise also. Then no diagonal also. Diagonal clash is also not allowed. Suppose if I am going to place queen 1 here, if I am going to place queen 1 here, I cannot place any queens here, I cannot place any queens here, I cannot place any queens in the diagonal also. That is a thing. So if I am going to take here, what will happen? So I cannot put here, I cannot put because diagonal clash, but I can certainly insert a queen 2 here. Okay, so that is one possibility. Next, the third queen I have to place now. So I cannot place here because the column wise clash will occur. Okay, can I place here Q3? It is not possible because the diagonal clash with Q2. I cannot place Q3 here because column wise clash with respect to Q2. And I cannot place Q3 here because once again there is a diagonal clash with the Q2. So that is why this particular combination won't work. So I have to change my strategy, I have to backtrack. Then I will try to insert Q1 here now in the first row, second column position. Next, I have to insert the Q2, that is queen 2. So here it is not possible because there is a diagonal clash. Can I insert here? Certainly not possible because column wise clash. Can I insert here? Once again there is a diagonal clash, but I can insert queen 2 here because there is no clash. Now I have to insert queen 3 now. So can I insert here? Definitely it's possible because no diagonal, no column and no row. So queen 3 we can insert here because here it is not possible column clash, diagonal clash, column clash. Next I have to insert the last, that is the fourth queen. So possibilities, first possibility is here because of course, but it is not possible because the queen 3 will clash with column wise and diagonal clash with respect to the queen 3. But here there is no clash because all of them they won't satisfy this criteria. So I can insert queen 4. So this is the one solution. This is the one solution I have preached here. The same thing we have to obtain. The same thing we have to obtain using the state space tree. How to draw the state space tree for this 4 queen problem? Now I am going to consider. I hope this has been understood by you. So I am going to draw this now. So now the time to draw the state space tree. Is it understandable? Come, get inside. So now, I'm going to draw the state space tree. Just focus here. So first I will start with we have 4 cross 4 grid here. So I will call this as a zeroth node. Zeroth node. I will call this as a zeroth node. Then the next node to be considered is like this. Once again, a 4 cross 4 grid. Okay. So I will call this as first node, and I will call this as second node. Okay, I will prove this. Let me find out how it works. So next, what I am going to do in the first grid, okay, in the first chessboard, I am going to insert the queen 1. Suppose this may be my queen 1 position. Next, can I insert here? Can I insert the next queen here? that is in the first row. Can I insert the queen 2 in the first row? Sorry, in the first column here, that is in the first row, second row position, first column. It is not possible because there is a clash here. Next, can I insert here? Here it is not possible. Can I insert here? Once again, there is a diagonal clash. So, in the 2 position also, I cannot make it. But here, definitely I can insert a queen. So that is why I have to prune. So this is pruning. Okay, so this is pruning. So means I have to draw another test row. Okay, so queen 1 is already here. Next, I have to insert queen 2 here. Okay, so what are the positions once again left? So here once again it is not possible. That is first column. It is not possible. In the second column, so once again there is a diagonal clash and row-wise clash. So second is also not possible. Then what about the third one? Because here I cannot insert because same column. Okay. Next, if you so that is third is also not possible. Fourth row. So column wise clash. Next, if you consider here, okay. So suppose if I am going to insert here, okay, Q3. So certainly it is not possible. So in fourth is also not possible. So now we shall go for the another alternative. Is there anyone waiting? Yarar waiting is the headache. So now I will check the next position once again. Q1 is here. I cannot insert here because once again column wise clash, diagonal clash 2 is also not possible. So third one definitely. So we have not reached it. So this one is possible. Q4. Sorry, Q2. So Q2 I can insert in the fourth position of the column. So now can I prune here? So let us find out. Okay. So now, so this is not possible for because already I have inserted here. Okay. So next I am going to prune this now. Okay. So once you prune this, okay. So this second row is possible. Okay. So second row is possible. So third row is not possible, you know. So second row I am going to prune now. So because okay, Q1 is here, so no clash with respect to Q2. I have to insert now Queen 3 and Queen 4. Now I cannot insert Queen 3 here because there is a column wise clash. Then can I insert here Q3? Definitely I can insert. Okay. So next, so this is not possible. 1 is not possible. 2 I have already inserted. 3 is not possible because there is a diagonal clash. 4 is column wise clash. It is not possible. So here onwards I can prune. Okay. But what happens, you know? Fourth queen I cannot place here. I cannot place here because column wise clash, diagonal clash, column wise clash. So definitely we have not reached to the solution. ನಮಗೆ ಸೊಲ್ಯೂಷನ್ ಸಿಕ್ಕಿಲ್ಲ. ಸೊಲ್ಯೂಷನ್ ಸಿಕ್ಕಿಲ್ಲ ಅಂದ್ರೆ ನಾವೇನ್ ಮಾಡಬೇಕು? ಹಿಂಗಡೆ ಸ್ಟೇಜ್ ವಾಪಸ್ ಹೋಗಬೇಕು. Back track. So I have went to the previous. Once again there is no possible solution. Once again you back track. That is go back to the previous stage. Then here also it's not possible. So back track. So you have reached the root node now. You have reached the root node. Okay. Now, once again, we will try to prune towards the right side because in the left side we have not obtained the solution. So possibility is only towards the right side now. So this is first node, this is second node, this is third node, this is fourth node. So next we shall go for the fifth node. Okay. So let us find out whether we are going to get any solution through the state space tree. in order to find out the NQueen problem, solution for the NQueen problem. So here I have inserted queen 1, that is first row, first column. Now I will change the position now. This is queen 1, that is first row, second column. So let us explore now further. Okay. So first row. So next first position, that is, can I insert here the next queen, because it is not possible in the one position because there is a diagonal clash. So now what about second position? Second position also not possible because column wise also we cannot insert. Now what about the third position? Once again there is a diagonal clash here, so third position is also not possible. So fourth position definitely I can insert. So because there is no clash here, so this will call pruning. This is not pruning enough. Pruning and growth ಮಾಡೋದು. Okay, so Q1 is here. I can insert Q2 here. Okay, so next possibility, so here can I insert queen 3? Definitely possible because there is no clash here. So this is pruning. So here it is not possible column wise clash. So second, not possible. Third, diagonal clash, not possible. Fourth, column wise clash, not possible. So this is the only place I can prove. Okay, so already queen 1 is here, queen 2 is here. So next position, so I can prune here, that is queen 3. Okay, now what about the second position? Second position is not possible because there is a column wise clash. Now this position we can clear, we have clarity because there is no clash. But here, once again, in the fourth position also, no. So one position is also no. So this third position is pruning place. Okay. So let us find out. So queen 1 is here, queen 2 is here, queen 3 is here, and definitely this is the position, that is queen 4. So we have reached the solution. Okay. So this is the solution. Okay. So this is how we can find out the solution for a given problem using state space tree and the So we call this as a state space tree. Okay. State space tree for NQueen problem. Okay. So exam perspective is really important. So kindly note down this. So this is what the state space tree. So what I have drawn on the board, the same state space tree, you can see here also. Okay. So yes, you can see here. So I have to name the nodes. This is the 6th node, this is the 7th, and this is the 8th node. Okay. So in the 8th node, we are going to get a solution. Okay. I hope this has been understood by all of you. So next is the Hamiltonian circuit problem. Okay. So what is actually to be a Hamiltonian circuit? Okay. In a Hamiltonian circuit is nothing but a circuit, what we can say also a cycle. Okay. So such a way that when you start a traversal from one particular vertex and you have to reach the same vertex back. Once you start your traversal, the place or the node from where you are going to start the traversal, you have to end at the same place. So this is so called as a Hamiltonian circuit problem. Okay, so how to solve this Hamiltonian circuit problem using backtracking ಅನ್ನೋದು ಇವಾಗ ನಾವು ಡಿಸ್ಕಸ್ ಮಾಡೋಣ. So ನಿಮಗೆ you can see some of the things which has been already written over here. That is the different thing. So first I am going to take a problem here, a problem for the Hamiltonian problem. So then we are going to take the solution, how to solve this Hamiltonian circuit problem. So Hamiltonian circuit problem. So here is the Hamiltonian circuit problem. How this can be solved anta. So first I am going to take an example. So example is, so A, we have B, then we have C, and this is D, then we have then now we are here. Okay, so this is a graph. So this is a graph. So now for this graph, I have to find out the Hamiltonian circuit. I have to find out the Hamiltonian circuit by using state space tree. Okay, so find out Hamiltonian circuit find out Hamiltonian circuit using state space tree. So this is the problem. So how to find out the Hamiltonian circuit? So once again I am going to narrate this. So a Hamiltonian circuit is a circuit. Circuit and then it is a cycle. Means if I am going to start any journey or any traversal from a given vortex, if I am going to start from A, my traversal must end at A only because it has to complete a loop, a cycle. Okay, so this is called as a Hamiltonian circuit. So now how to find out the circuit in a given graph? So this is a graph. Okay, this is a graph. So how to find out the Hamiltonian circuit in this given graph using state space tree, because state space tree is one of the mechanism present in the backtracking. So how to find out? Let us find out. So first I will start my journey at A. Just assume I am going to start my journey at A. So this is where I have started. So I will call this as a zeroth vertex. I will call this as a zeroth vertex or zeroth node. Next, I have to go. So what are the adjacent vertices for A? When you consider A, there are three adjacent vertices, like we have B, like we have C, and as well as we have D. So there is a tie between B, C and D, because once you start at A, either you have to reach B, or you have to reach C, or you have to reach D. But how to break the tie? So which one I have to visit the next vertex means I have to go for alphabetical order. So if you choose the alphabetical order, definitely after A you must go for B. So my next vertex to be visited is B. So I will call this as 1, vertex 1. Okay. Next, once you start your journey from A to B, once again when you reach B, you have so many two alternatives now. One, either you have to go for C or you have to go for F. Once again, you can break the tie by using the alphabetical order. So definitely you have to go for C. So I will go for C. So I will call this as vertex number 2. Okay. Next, I am at C now. I am at C now. C. Once again, I am going to explain the Hamiltonian circuit. A Hamiltonian circuit is a circuit or a path in such a way that you have to traverse all the vertices. Each and every vertex you have to traverse, and you have to go back to the same vertex from where you have started your journey. Suppose if I am going to start A, I have to traverse each and every other vertices. You cannot skip any one. You cannot skip anyone. You have to visit each and every vertex. Then you have to reach back to the same vertex, that is A. So now I am at C now. So possible alternatives is D and E. Of course, if you choose alphabetical order, you have to go for D. Okay, so I will call this as third vertex. I will call this as third vertex. Next I have to go for after D. So I cannot go back to the A, because if I go back to the A, it becomes a circuit, but I will skip E and F. But it is not going to follow the definition of Hamiltonian circuit. So it's a violation of Hamiltonian circuit, because Hamiltonian circuit tells that you have to visit each and every vertex. So that is why I have to go for. So first let us find out after D. After D I will go for E. So I will call this as fourth vertex. So now I am at E now. I am at E now. So what are the possibilities? Definitely only one possibility left for me now. I have to go for F. So this is fifth vertex. Now what happens? I can declare this as a dead end, because I cannot go anywhere now. I have been stuck here because F is the end. I cannot go back to F because B, because B is already visited. So you can visit a vertex exactly only once. So now I cannot come back because E is also already visited now. So it means I have been stuck here. So I cannot go back to A, because my objective, once I start my journey on my traversal, I have to reach back the same vertex from where I have started my journey. So that is why I have reached the dead end now. So if you reach a dead end, there is no solution. So it means you have to backtrack. You have to go back. So you have to go back to E. So find out the possible solution, whether it can go anywhere from here. So once again, it's not possible, because either you have to only go for F. So next you go for D here. So any possibility? Yes, there is a possibility A. But if you reach A, what happens? You can skip E and F. So that is why D is not also an alternative. Next, you go one further step, that is C. Is there any alternative in the C? Instead of going to D, can I go for directly E? Is there any possibility, yes or no? So there is a possibility. I can go E also. From C, instead of going to D, I can go for E. So I call this as a sixth vertex. Okay. Next. So next possibility is, so after I have reached E, so only two options left for me. Either I have to go for D, or I have to go for F. So I have to go for D, or I have to go for F. So I will call this as 7th and 8th vertex. And D now in this situation is also dead end, because if you go to D and if you reach A, you can skip F. So that is why this is also a dead end. And on the other hand, if you consider F, you cannot reach back A. So this is also a dead end. So C is considered to be a non-promising vertex. And in promising ಮತ್ತು non-promising. Promising ಅಂತಂದ್ರೆ ಇಲ್ಲಿಂದ ನೀವು ಮುಂದೆ ಹೋದ್ರೆ ಡೆಫಿನೆಟ್ಲಿ ನಿಮಗೆ ಸೊಲ್ಯೂಷನ್ ಸಿಗುತ್ತೆ. So those type of nodes or vertices, we can call them as promising. On the other hand, see what happened now? We have never reached a solution. So we can declare C as a non-promising. So now you go back to the E, the back backtrack to E, once again backtrack to C. Next we are here now. Okay, so in C, since C is considered as a non-promising, once again you backtrack to B now. Now I have reached here, this place. Okay, next find out any other possibilities in such a way that I can reach to the Hamiltonian circuit. So now in this case what happened? After B I have visited C, isn't it? So after B I have visited C. Any alternative for this? After B? So there is a alternative called as F. So call this as the ninth vertex. Call this as a ninth vertex and start exploring now. After F, what are the possibilities for me? Only one possibility, because from F I can only go to E. So call this as E and call this as the 10th vertex. Okay. Next, after E, I can go to C, I can go to D. So there are two possibilities. How to break the tie? Go for the lower number, that is C. So call this as 11th vertex. Next, after C, I can go back to B, I can go back to A, I can go back to D. So if I go back to B, it is not possible. B is already visited. I cannot go back to A because if you go back, D will be skipped. So that is why. So go back to D. Go to D. So that is 12th vertex. Next, after D, only one option left. That is D. So 13th vertex. Okay. So this is the solution. Okay, so how to draw the state space tree? So they may ask a question, define Hamiltonian circuit and solve the following graph and find out the Hamiltonian circuit by using state space tree. So the solution is A, next B, next F, then we have E, then we have C, then we have D, then at the end we have A. Okay, so this is the Hamiltonian circuit problem. Okay, so the third problem, so this is all over Hamiltonian circuit ಇಲ್ಲಿ ಮುಗಿತಾ ಇದೆ. So next to sum of subsets ಅಂತ ಇದೆ. So ಏನಿದು sum of subset? So I'm going to explain this now. So I'm going to wrap this now. So next is sum of subset problem. So what is this sum of subset problem? So let us find out. Okay, so sum of subset problem ಅಂತಂದ್ರೆ ಏನಪ್ಪ, we have a set here. ನಮ್ಮ ಹತ್ರ ಒಂದು set ಇದೆ. We call this set as S ಅಂತ ಕರೀತೀವಿ. Okay, so this S is nothing but S1, S2, so on Sn ಅಂತ ಕರೀತೀವಿ. So this is a set. Yes, and S1, S2 are called as subsets of S ಅಂತ ಕರೀತೀವಿ. Condition ಏನಪ್ಪ ಅಂತಂದ್ರೆ the sum of these subset must be, that is S1 plus the elements, whatever the elements present in the subsets, okay, they must be equal to the sum D anta karikare. Okay, find a subset of a given set S of n positive integers whose sum is equal to the positive integers of D. Okay, like for example, if you take S1 plus S2, which must be equal to some positive integer D anta karikare. For example, ಈಗ ನಾನು ಒಂದು example ತಗೊಳ್ತೀನಿ. S is equals to 1, 2, 5, 6, 8. 1, 2, 5, 6, 8. So this is S. Okay, just like this is also S. Now D is also given. D is equals to 9. D is equals to 9. So now we are going to find out the combination of these numbers in such a way that when you sum up them, the sum becomes 9. So that is the thing. So what are the different combinations? Okay, so like the first one, S1 is equals to, so we have 1, 2 and 6. Can I consider this 1, 2, 6 as one of the subset of the given problem? Can I consider? Yes, definitely, because when you sum up 1 plus 2 plus 6, 1 plus 2, 3, 3 plus 6, it is equals to 9. So any other subsets possible? So 1 comma 8 is also possible, because if you sum up 1 and 8, definitely once again you are going to get. So these are the any other combination? I think no, only 2 combinations. So this is how we can find out the subset sum of subset problem. So once again we have to draw the state space tree for this. So how to draw this? Let us find out. So first I am going to start with the 0. Okay. So 0 means nothing I have taken, nothing I have taken. So 1 is with. So the set is, what is the set? Is, okay. So this is the new problem they have given. So 3, 5, 6, 7. 3, 5, 6, 7. So this is the set. D has been given value as 15. Second problem. Okay. So D has been given 15. So any subsets we are going to get S1 is equals to. So any other solution sigutta? D comma 5 at 7. 3, 5, 7. So 3 plus 5 is 8. 8 plus 7 is 15. Isn't it? So this is one possibility. So how to find out using state space tree? No data. So first to 0 tagotadini. So one to left side and with 3 tagotadini, because first element is 3. So right hand hodra without without 3. So with 3 without 3. Left to with inclusion anta. Right side exclusion. Adar nanti tagolak barala. Suppose if I add 0 to 3, what happens? 0 plus 3 is 3. Without means 0 as it is. 0 as it is. Okay. So next 3 argument and next 2, I have to go for next element, that is with 5 attack without 5. So with 5 attack 3 plus 5 8 attack. So without attack 3 will be kept as it is. Okay. So next I will go with 6. Okay, with 6. So another one is without 6. So if I go with 6, 8 plus 6 becomes 14. Okay. Next, here if I go, this will become 8. So next, the next element to be taken here is 7. If I take 7 here, 14 plus 7, which is 21, which is greater than 15. So this is not a solution. So on the other hand, if you go here, if you go with 7, you are going to get a solution here. This is a solution. Yes or no? So this is a solution. So on the other hand, if you go without 7, so you definitely once again 8. So this is not a all solution because 8 is less than 15. So you have to backtrack. You have to go back. So once you reach here, okay. So once again there is an alternative here. So for 3, without 3 and the other next is with 5. Isn't it? Without 5 with 3 there. So after 5 what is 6 here? Alva? So we have to go for with 6. This is without 6. If you go with 6, it becomes 9. If you go without 6, it becomes 3. So next after 9, so we have the last element is 7. So 9 plus 7 is 16, and 16 is greater than 15. So this is not a solution. Then what about here? The last element is 3. 3 if you add here, what happens? So this is So 3 alpha. So 3 plus 7. So 3 plus 7 is, that is 10. Once again, 10 is less than 15. This is not also a solution. So go back, go back, go back. So once again, you have to reach the root node, because in the left side, only one solution we have obtained. So let us find out whether any other solution exists in the right subtree. Okay. So so I have to go for now two alternatives, with 5 and without 5. With 5 means 5, without 5 means 0. So once again, there are two alternatives, with 6, without 6. So the value becomes 11, the value becomes 5, and last element is 7. 11 plus 7 is 2. So once again, 18, which is greater than 15, which is not possible, and whatever here. So 5 plus 7, that is 12, which is less than 15, once again, which is not possible. So go back, and you can prove here. So without 5 means we have to go for with 6. With 6 means this is 6, this is without 6, means 0. Okay, so 6 we have reached here. So 6 plus 7 is 14, that is 14 is less than 15, and if you consider 7, without 6 means 7 plus 0. 7 is once again less than 15 in both the case. So no solution exists in all the cases. Okay. So this is the only one solution we can extract using state space tree. So this is once again a state space tree for sum of subset problem. Okay. So now I'm going to execute the programs of these two. Okay. So find out the output version of this. The same tree is also, you can see here. So I hope we can see it, Arvasi. So I'm going to first run the NQueen problem. So this is NQueen. So I'm going to compile this. I'm going to execute this now. So number of queens. So I have taken 4 as an example. 4 queens I have solved. Okay. So you can see the output. So XX means the empty spaces. Okay. So we have 2 type of solutions for this. We have 2 solutions, and one I have drawn using the state space tree. Okay. So we have 2 solutions. Solution 1, solution 2, both of them. And already I have shared this program in the group also. You can execute them at your home. Okay. Shall we take next one? So this is sum of subset. Okay. So I'm going to compile this. I'm going to execute this. Enter the number of elements. I have taken two problems. First problem I have taken is how many elements? 1, 2, 5, 6, 8. Totally how many elements? 5 elements. Enter the elements in ascending order. First, I will take the first example. 1, 2, 3. Sorry, I think 5. 5. Then we have 6. Then we have 8. What is the sum? No. Second problem is 15. 9. First problem is 9. So only, I think only one solution is present now. Oh, two solutions. Okay, sorry. 1 to 6 and 1, 8. If you sum up 1 to 6, 1 plus 2 plus 6, you are going to get 9. 1 plus 8 is also 9. Okay. So this is the first problem. Second problem, once again we will execute the program. So enter the number of elements. How many? This is there on the board now. So how many elements? 4 elements. What are the elements in ascending order? 3, 5, 6, 7. 3, 5, 6, 7. So sum 15. So only one solution is present. 3, 5, 7. See, you can see here 3. Okay, you can see here 3. So this is without 6 means. So 3 and 5. 3, 5 and no 6 because without 6 and with 7. So 3, 5 and 7. Okay. So this completes your backtracking. Okay. Okay, dear students, this completes your backtracking. In my next class, I am going to discuss on branch and bond. Okay. So branch and bond ಮಾಡ್ಬಿಟ್ರೆ majority 99% ಮುಗಿದಂಗೆ. So next class ಅಲ್ಲಿ branch and bond ಮಾಡಿ ಮುಗಿಸ್ತೀವಿ. Okay. So today I am going to stop here. So I am going to share all these materials in the YouTube. So suppose somebody is missing, you can watch them later. So thank you so much. Give your attendance to the chat box.